record on this computer. I'm recording. They've changed Zoom for me a little bit here, so things are in different places now. Just when you get used to one set of controls and where all the buttons are, they move it. All right, so I wanted to just finish up with a couple things on Compton scattering from last class. We ran out of time when we were doing one of the problems. It came to me to show, and so what I'm going to do, and hopefully you'll see this, is I have an animation from that King Center in Edmonton, Alberta, up in Canada. They put together a pretty amazing set of animations, so I want to share that with you. And it does clear up a question that was in my mind, maybe not in you all's mind, but in my mind about, let's go to, which one do I want to go to? Apparently I have multiple ones open. So let me close this and back out of that for just a second and share screen. Okay, now I only have one. Share that with you. And what you're seeing here is going to be in a second a mock-up of Compton scattering. Let me just show you what it looks like. Okay, so there comes the photon in. The photon gets scattered at some angle. Right now I've got the angle set to 45 degrees, and you can see the wavelength of the incident photon. And this thing comes with the ability to show data, and you can see the photon was scattered. It's saying my screen share is paused. So let me stop. Let me try again. Okay, let's run it again. Hopefully I can do that. There it is. All right, so hopefully you saw the photon come in, a photon went off at a 45-degree angle, and then that electron that was at rest that the photon hits, it recoiled off at some angle. Somebody give me a thumbs up if you saw that. All right, excellent, good, thank you. So just a couple things. The wavelength I had going in was just about 4 picometers. I couldn't get it any closer than 3.99. And you should expect that the final wavelength has less energy, right? I lost energy to the electron, and so I have less energy. That means the final wavelength went up. That's 4.7 picometers, right? So incident wavelength is 4 picometers. The one exiting is 4.7. That represents a loss of energy. Where does the energy go? That electron that was sitting right there recoils off, and you can see that the angle it went off was at 56 degrees. Let's just change things up just a little bit here. Let's take the wavelength, increase it by 10. So as close as I can get to 40 might be that. And again, launch it again. And you can see I do get a shift in wavelength. It goes up just a little bit, okay, a fractional shift by the Compton wavelength, what we called. And you can see the angle of the recoiling electron is significantly different, okay. One of the things I liked about this is I was having a little bit trouble last class visualizing what is a glancing angle, what is a bounce back angle, and this animation answers that question for me. The kind of glancing angle would be this one, right? And this animation calls that 0 degrees in Compton's equation, and so I think that is the correct way to measure an angle. Actually, I had it 1 degree, so you can see that exiting angle is 1 degree. And then the problem we ended up with on Wednesday was the bounce back problem, okay, where the photon just bounces back. And I can't get exactly 180, but this was the problem we were doing, right? Photon comes in, bounces straight back, electron goes out. And we ended on that. And I didn't make perhaps clear how difficult mathematically, algebraically, so it's not like we're doing differential equations or anything like that, how complicated it is to figure out what the velocity of that recoil electron is. You can see it, this app just calculates it, doesn't it? It tells you that the beta is 0.11 for this particular example with that particular incident photon wavelength. All right, so what I want to do is stop sharing this and just finish up with a little bit more time to make sure that it's clear how you can calculate what that what that final velocity of the electron is going to be. Okay, and so I'm going to start sharing my solution with you. There's Acrobat, and the top piece there is exactly what group one, I guess, did last time. Okay, so group two, let's make sure we got the pieces of how you do a Compton scattering problem. I guess you can always use this equation. The difference in wavelength is equal to the Compton wavelength, H over MC times 1 minus cosine of theta. It's on an equation sheet. You can always use that. But because we're physicists, we can always go back to something more fundamental like conservation of energy and conservation of momentum. And so I looked at a before and after picture, right? Before I have the energy of the incident photon and the electron sitting there at rest. And then afterwards, I have the electron going off with some speed u, and my job is to figure out what that speed u is. And the photon gets bounced back 180 degrees, just like in the animation a second ago. And the only thing we know about this problem to start with is what the energy of the incident photon is. And we're told it's an X-ray. We're told it's zero point 0.3 MeV. You could calculate the wavelength right now if you wanted to from that. HC over the wavelength is equal to zero point 0.3 MeV, right? You can just calculate what the wavelength is. But let's try to write conservation of energy, conservation of momentum, manipulate those just like Dr. Tech would have had you do in a conservation of energy, conservation of momentum problem back in PHY211. All right, so energy of the photon, Hc over lambda, already said that. We know that. It's a number. It's 0.3 MeV. The rest mass of the electron just sitting there, okay, 0.511 MeV. Know that too. That's a number I can look up on a table. But we don't know anything about what the wavelength is after the collision, right? I mean, I go to that King's King's University simulation and figure it out. They'll do the math for us. But at this point in the problem, we don't know what the final wavelength is, and we also don't know what the final energy of the electron is after this collision. Okay, and so I just left those as unknowns. Momentum, on the other hand, um, Planck's constant divided by wavelength. Hopefully, you've come to accept that that is the momentum of a photon. Yeah, it's an odd thing that a particle with no mass, like a photon, has momentum. But if you think about it, in PHY 112, one of the last things we did when we were talking about optics is we were talking about radiation pressure from electromagnetic radiation. And this is exactly what we're talking about. Photons have momentum, just like bullets have momentum. And so one of the things that is being investigated seriously today is a spacecraft powered on a sail by light coming from the sun, because all those photons of light coming from the sun would impinge on this, would have to be a monstrous sail. But eventually that momentum would be converted into some kind of kinetic energy, right? You can actually push the spacecraft if light particles from the sun are allowed to hit a large area, and it can actually move something. Now, initially the forces would be minuscule, but left to integrate over time, you can very quickly get up to very fast speeds, very quickly being in maybe a year or so. One of the problems with a propulsion device like that, because that's what we're describing, it's kind of like the sailboat of outer space travel. The problem with it is it's a one-way trip, isn't it? How do you get back? That's the problem. You need another light source, another sun someplace else, and you'd have to direct yourself back to our solar system using that. And so it's a little bit of trouble. But in any event, massless particles like photons have momentum, and that's one application, this radiation pressure thing. Okay, so the momentum of the electron, though, it's at rest, zero. And then as the photon bounces off the electron and comes back, it has momentum coming back, just a different wavelength, and it's been reversed in the direction. That's why in line C there, I made it a minus h over lambda prime. Okay, and wavelength changes. That's the significance of that the prime. Okay, and then I guess that's our momentum right there that we said for special relativity. That would be the momentum of the electron, and I left it in the positive direction. All right, so the things I don't know. What don't I know here? I don't know that. And I guess I don't know that. And inside of gamma, I don't really know gamma, because inside of that would be the speed of the electron, right? Everything else here, I think I know. And that's often a problem in physics. I'm doing it with my 101 students right now, where they have Newton's second law problems, and they have two objects, and they maybe don't know tension and acceleration, right? And so you got to combine them somehow. Any way you want is correct if you can come out right. When I looked at this, the simplest thing I said is, well, let's just multiply the momentum equation by the speed of light. So multiplied by c right there, multiplied by c right there, multiplied by c right there, and then rewrite it, and then just bring down the energy equation. And hopefully you can see why I did that. If I add these two equations, one of the things that I don't know, the wavelength after the collision, goes away. And that was the strategy behind it. There's, like I said, other ways you could have solved the problem, but that's it. And so I put these two folks together. That just becomes 2 times the initial energy. Remember, we know that. That's in this problem, zero point 0.3 MeV. All right. Let's see. What else do I know? I know this too, don't I? That's, like I said, 0.511 MeV. So we're good to go there. Add them up. Point 0.1 or 1.111 MeV is the sum of these two numbers. And so I know what the left side of the equation is. Now look at the right side here, what's left, because that canceled. And what's left is the thing I don't know, the speed, which is also hidden in gamma. It's right there, it's right there, it's right there. But I think I can factor out the gamma, left with that term, MUC plus MC squared. That's now just a constant, right? So we got that. Let's see. So what I did is I factored out MC squared because, like I said, I know it. It's a constant. And this is a little wacky, but that leaves that guy right there. Okay, but that's beta, isn't it? That was my motivation for doing it. So that's 1 plus beta and this is 0.511 MeV. And of course, gamma is containing the unknown speed I don't know. And again, often different ways to approach this. But so I'm left with this number right here and this number right here. Those just become a number. So I divided it out, and that's where I got the 2.17. That's 1.111 divided by 0.511, basically doubling it. Okay. And then what's left, I actually wrote out what gamma is, 1 over the square root of 1 minus beta squared, beta being u over c. So essentially what I have is 1 plus beta over the square root of 1 plus beta, right? And that has to be equal to this number right over here. And so you can see the algebraic difficulty of that, hopefully. I just very quickly maybe even mention it. When I do this, the answer is beta is equal to 0.651. And you may ask yourself, how are you going to do that problem if it, say, shows up on an exam or a homework? Okay. And it's a tough question. If you have a TI Inspire calculator or you go to Wolfram Alpha, you could just say, here's my equation, 2.1742 dimensionless, right? Because we divided the MEVs away, is equal to 1 plus beta over the square root of 1 minus beta squared. Solve for beta, please. And a lot of calculation devices will do it. Back in the old-fashioned days, like when I was a student, okay, here's what you had to do. And so you should just have an appreciation for this, maybe. I don't know. Let me get rid of my drawings here. There's that equation I had to solve. And if you do it out by hand, using, like, say, the quadratic formula to solve what turns out quickly to be a quadratic equation, right? You got beta squared in here. That's how much work you have to do to get the 0.511. And so this is the kind of effort that the calculation device saves you, but you do get that answer. Okay. And I'm not going to go through this, but trust me, I did the algebra right there. And sure enough, that's how I got beta being 0.651. So, a little over half the speed of light is how fast this electron is recoiling away. And so if there's any doubt right there that you have to use special relativity energy equations, it's resolved, right? We said anytime you're over about half the speed of light, you can't use classical energy expressions any longer. They're just not accurate anymore. Okay, but one other way, and that's why this is titled alternate methods here. I suppose it might be shorter. You could have gone with just Compton's equation, right? Because we gave you enough information to know what the initial wavelength is. Okay, you could have solved for what the final wavelength is. Okay, and solve for that. And once you know the final wavelength, I guess, what did I do here? Oh, no, I lied to you, I guess. That is the change in wavelength, isn't it? So then from that, with the initial wavelength, then I can get the final wavelength. All this line is what the change in the wavelength is, what the shift is. And so I have to add this to that to actually get the final wavelength right here. And then you can get the energy out of that because it's equal to hc over the wavelength. And then now I know what the final energy is. I know what the difference in energy is. We started with that amount of energy. We ended with that. So the photons change in energy is the difference. And that energy, of course, goes into kinetic energy. Now, you may be concerned, what about rest mass energy? Well, it was on the other side of the equation too, right? Because the energy of the photon initially plus the rest mass energy of the electron is equal to the energy of the photon final plus the total energy. So it's mc squared of the electron plus the kinetic energy of the electron. I just canceled those and found the difference between those two guys, and that was 0.162 MeV. And that allows me to then just solve for what the kinetic energy must be. And then ultimately I have to solve for gamma. The good news is I'm only solving for gamma, right? And gamma turns out to be 1.3172. And then from that, as we've done before, you can get beta. And sure enough, I get the same value of beta, 0.65, a little over half the speed of light, again, is the speed of the recoiling electron. Any questions on that? We were sloughing through it pretty quick last time, and wanted to make sure that everybody saw that. And I think we pretty much handled the first problem that we did pretty straightforward. It was just plug and chug into Compton's equation, but we went pretty quick through the second one, and there were some technical difficulties as I recall as well. But I didn't want to leave you with the impression that we were done with it. Last chance on Compton scattering. All right, moving on then. Moving on. I don't see anything in chat either. Where is chat? They moved. Oh, there's chat. Nothing in chat, so everybody seems to be happy. All right, so we're done with Compton scattering. I've got some polling questions on the topic for today. It's now the third time we're looking at photons' interaction with matter, right? You may think about it a third time. What are the other two? Well, the first time was photoelectric effect, right? Photons came in, visible light sometimes, fairly long wavelength, low energy photons, hits a photoelectric material and electrons get emitted, right? Compton scattering was, of course, the second one. Photon comes in, hits an electron, changes the energy and the wavelength of a scattered photon, and kicks an electron off at some high speed. Photoelectric effect is the third type of interaction of photons with matter. And so let me slide over to PowerPoint here gracefully. All right. And of course, I have polling questions. There's the first one you can think about. And I just got to find, there it is, first pair production, and we'll launch it. And this is the big picture question, I guess. Energetic photon undergoes pair production. It interacts with matter in a way, and we'll talk about how in just a second. What gets produced? There we go. Everybody's got it. Piece of cake. I say everybody, the first four people in have it. How's that? One person's conserving charge, but not mass. Waiting on two more. What gets produced? All right, everybody's in the poll, and majority wins here. And so if you think about chemical reactions, there is a chemical reaction for for pair production, gamma. Why? Because gamma radiation, all it is a photon, okay? It's a very high energy photon. That must mean that, oops, wrong way. Sorry here, gotta erase that. Need the reciprocal. Energy, which is equal to hc over lambda. If energy is big here, really big number, That must mean it's a pretty short wavelength. And it's in this part of the spectrum that we call gamma radiation. That's why we use gamma. In any event, it goes and it produces two objects. One of them is the electron, okay? But the other one is not a proton. It is something called a positron. A positron is something that is exactly an electron, just with a positive charge. Now, in both my pre-lecture video and in the reading in the book, I don't think we make too big a deal out of this, what this positron is. In fact, we just say, hey, things produce them. It's a piece of antimatter. Okay. It doesn't hang around in our world very long because it is antimatter. And you can read all kinds of bizarre theories about what antimatter is. One of them that seems to have credence is it's regular matter, it's just moving backwards in time. Okay, and so when it interacts with regular matter, like an electron, we're going to talk about annihilation here as well. Okay, so that's what a positron is. It has the same mass as an electron, and that's it. All right, questions on that? That's what happens in the middle of, out of nowhere, out of energy, not in the middle of nowhere. There, we'll talk about that in just a second. But energy in a photon gets converted into mass. Okay, E equals mc squared, exactly like Einstein predicted. Energy manifests itself on just spontaneously into two particles, a positron and an electron. I find that amazing. I mean, the math is pretty simple here, pretty straightforward stuff, but that it happens is sort of bizarre. Here's the next question. Stop sharing this. Always at the bottom, launch it. And so can that reaction, draw the positron first this time, can that happen in empty space? True or false? Yes or no, I guess. All right, everybody's in. Unfortunately, one person, nope, you missed it. Okay, share results. The reason we said that can't happen, and review the pre-lecture video yesterday if you missed this, is in order to conserve both energy and momentum simultaneously, okay, in order to conserve energy and momentum simultaneously, some momentum from this incoming photon has to go someplace else. Okay. Otherwise, the momentum energy balance can't be true simultaneously. So, what we say we need is we can have this happen near a nucleus or an atom. Okay. And so then the two particles get created, the electron and the positron. Okay. But in order to conserve momentum, this thing must get kicked a little bit. And you can make both energy and momentum all balance if you do that. Without this guy, it's impossible to have both energy and momentum conserved simultaneously. And that's just a mathematical artifact. I showed that in the pre-lecture video. It just becomes a fact now. We accept it. Okay. Questions on that? You guys are just too easy here today. Not going to pin me down on anything. Here's the next question. And I'll stop sharing. Oops. Stop sharing. And go to the third one. Okay, mass of an electron I'm giving you here. And so how much energy must be in a photon in order to make this work? And please don't go reaching for a calculator. Four or five. Thought we were going to get 100% here. One more person. Everybody's in, and I'll share the results. All right, look, if this guy has a rest mass of 0.11 MeV, and so does the other guy, that means at the end, you have to have at least double that. 1.022, I guess, would be the number of MEVs just in rest mass. And that would give it no kinetic energy, right? Because they would just get created and sit there next to each other and probably very quickly annihilate away. But if you don't have that much energy in this gamma, this can never happen. So the absolute minimum energy you need is that. And of course, if that's exactly the energy of the incoming photon, the positron and the electron will get created and go nowhere because they'll have no kinetic, there'll be no energy left to give them kinetic energy to move away from their creation site. Okay, so that's it. Sixia, good work. Stop sharing. We'll move on to the next one. Move on to the next one here. Launch our poll. Now you got to do the math the opposite way, don't you? How much kinetic energy will be left? I didn't do that. Stop it. How much energy will be left if a 1.5 MeV photon comes back? And remember, our rest mass energy of a positron or an electron is that. That's an M. It's just a real lousy M. Think conservation of energy here. One more, waiting on somebody. All right, everybody's in. I'm actually confused by this, the bottom two, C and D. Look, if this has 1.5 MeV right here, and we just said the rest mass energy of these two guys, which is kind of the minimum energy of the incident photon, we just said that's 1.022 MeV. Anything left then has to be kinetic energy, right? And so the kinetic energy is the difference between these two numbers. And I think the difference between those two numbers is 0.48. Now, if you pick C, you're saying you basically think that gets split in half, 0.75 MeV to both. Possibly, but remember, if you go 0.75 to it, 0.511 of that is just rest mass energy. So only the difference will be left over for kinetic energy of that particular particle. By the way, there's no guarantee that the kinetic energy will split evenly between the two particles that are created. Okay, that kind of depends on what the position of that third thing that has to be in the vicinity, that heavy nucleus that has to be there to help conserve momentum and energy. That will be a big factor in how the energy, the final kinetic energy, is distributed between the positron and the electron. No guarantee it'll be equal. All right, and 1.5, nope, it doesn't all go into kinetic energy. It has to create the particles. Energy gets converted into mass, and then whatever's left over becomes kinetic energy. And hopefully that makes sense from a conservation perspective. All right, a couple more of these. We'll show you what everybody did there. 4 people, half the people went on the wrong direction on that one. A little concerning. Let's move on to the next one. I think people are catching this one. Got it, I think. One more. All right, I'll share the results with you. And I think absolutely the majority wins here. If you're looking at increasing energy this way, at low energies, photoelectric effect, right? Why? What was the work function for photoelectric effect? If you recall, 5 EV might have been a work function, very low energies. So a photon comes in, as long as it has greater than 5 EV, kicks off an electron. In the mid-range here is Compton. And we said Compton scattering took place with X-rays, things that were like, oh, I don't know, 30 picometers. And by the way, this could correspond to visible light, right? It could be like 600 nanometers. So significantly bigger, that's an N, significantly bigger wavelengths, significantly lower energies. Compton was X-ray in that range, okay? And then we said photoelectric effect, which oddly, I'm sorry, not photoelectric effect, pair production, PP as opposed to PE, that you needed greater than 1.02 MeVs in order to see photoelectric effect. So this guy right here, Compton's possible, photoelectric effect is. We'll talk next week when we talk about the Bohr model. We can excite an atom. That means we can take an electron in the atom and take it to a higher energy level. And we'll talk about what energy levels and electrons are next week, but you can't do pair production. So D is the right answer. And that gives you kind of the big picture, I hope. Last one, I think. Yep, one more. And then we'll get to the worksheet here. Now we're talking about the other effect, where the electron and the positron, I said it in that order, so let's write it in that direction, they kill each other, and you get photons. Which one's not possible in free space? Two more people. Got 6, 7. All right. All right, everybody's in. And I agree with the majority here. In free space, it'd be really hard for one photon going away to conserve momentum. I'm trying to figure out how would two electrons, I'm sorry, an electron and how would they perfectly balance both energy and momentum? And so that'd be hard with one. I could see how perhaps with a third one, you can balance. The most common thing is that two photons go away in opposite directions, and that's meant to be a squiggly line. That happens the most common. And in fact, a little discussion in the pre-lecture video of PET scans, a medical imaging device, where they inject radioactive material that is a positron emitter. It combines with other electrons it sees in an organ in your body and immediately emits two photons, most often in this configuration, okay, two photons, as opposed to three. One's possible, three's possible, but one requires another atom or something else there in order to both simultaneously conserve momentum and energy. So that's the bottom line on it. All right, any questions on any of that? All right, then I'm going to stop sharing that with you, and we'll move over real quick to the worksheet before we break up into groups here. Where is it? There's Acrobat. 3 questions. There it is. Move to the other. First one is to determine the threshold wavelength. We already talked about what threshold energy is. So I think group 1, you kind of get an easier problem, figure out what the threshold wavelength is. Group 2, we'll see who you are in just a second. photon with a wavelength of that many picometers. Notice how short it is? Okay, that's in the gamma regime, that many picometers, as opposed to X-rays, which might be 20 or 30 picometers. Okay, so that creates positron electron pair. You want to determine the kinetic energy. If the kinetic energy of the positron is twice that of electron, remember we said it doesn't split 50-50. This is one such example. And then the last one, this is an annihilation between a positron and an electron, and it's creating two photons in order to conserve both energy and momentum. We want to find the kinetic energies of the electron and the positron before the collision. All right, so that's what we're going to go do here for about the next, I don't know, 5-10 minutes. Where's my breakout rooms? There they are. So group.
Is there no fourth question? We don't have to do the last one?
Do I have a fourth one? Oh, yeah.
Whoops. No, it's fine.
There's another annihilation question. Yeah, so let's go to 4 groups then. Yeah, this one, positron, they're at rest. They get 3 photons out of this one. Yeah, so let's go to 4 groups then, and just a slightly different group. All right, so group 1, Amaya and Anaya. Group 2, Justin and Shriha. 3, Max and Sam. 4, Prince and Sayed. Okay, so those are the 4 problems. And the 3 and 4 are pretty much the same as our 1 and 2. 1 and 2 are production, 3 and 4 are annihilation. See you in a bit. Yeah, I added that.
Equation.
Really?
Yeah.
Nice. Less work.
All right, I think you guys can write on that whiteboard if you want. Do you have a number? You have the easiest problem, I think.
Yeah. Isn't it just going to be H over 2m EC?
H over 2m. Yeah, I think you can do that. I think that works, right? I don't start that way, so go ahead, show me the first equation.
For the pair production threshold relation, I think it's I started with, I think E equals HC over wavelength.
Okay, yeah, that's where
And then
I would start.
I just manipulated it.
Yeah.
And should it be the equal sign, or yeah, it should be the equal sign.
Yeah, the reason it's a threshold is because you're not having any kinetic energy at the end, right?
Yeah.
HC over lambda. Yep. Yeah, I know I have trouble drawing that too. And so lambda is equal to HC and E is 2mc squared, right?
Yeah.
And that's why I think you canceled one of the speed of lights when you were talking just a second ago, right?
Yeah. But I guess you don't even have to.
Yeah, I wouldn't. I would just leave HC as 1240, right?
Okay.
1240 EV nanometers and divide by 2 times 0.511 MeV. I'll let you go. You guys got it.
Thank you.
You bet.
Yeah. C squared. Justin? plus Ke positron plus Ke electron.
Yeah, I agree.
Yeah.
Absolutely.
Now, the sum of the rest mass energies is obviously like 1.022 MeV by c squared.
Yep.
And Hc by lambda will just be 239.
Yeah, use that number right there. Right there.
Oh my god, it's a very big number.
No, because remember HC is 1240.
4.13 mega electron volt. I think
Is it 1240 EV?
It's EV, yeah, 1240 EV nanometers though, right?
Yeah.
And you got picometer as opposed
is
to
like
nanometers up in the numerator. I'm writing over here.
So that'd be
Right, this is EV nanometer right there. Yeah. But you got it. And then the only thing is, what do they tell you? The which is double the other. Kinetic energy of the positron. So that'd be this one. This guy is twice the kinetic energy of the electron. Right?
okay.
So plus kinetic energy of the electron. Yeah. So when you get that number, I think you said the right thing right there. That's 1.022 MeV.
Yeah.
And then away you go. All right. I'll leave you alone then. All right, let's see if I agree with you here. 1.489. Find the kinetic energy electron before the collision. Yeah, I agree with that.
Cool.
See what you did. You had electron about equal energy head-on collision, 2 MeV photons. So that's where you got the 4 MeV. Yep. I think I agree with that. Yeah. And then it splits between the energy of the positron and the electron before the collision. Okay. And then you subtracted off the rest mass energy, and you're left with what the kinetic energy is. Yep, exactly. Sounds good.
Cool.
All right, let me just check on the last group, and then we'll come back and talk about our problems.
All right. Thanks.
That's what I was trying. I mean, I'm just a matter of time. I'm not sure.
Yeah, we're getting. Okay, so
I'm just looking for the equation that gives us mega electron volts.
isn't that like don't you just use A equals MC squared and then 1240? No, I don't think so.
Yeah, no, that's what you got.
Oh, really?
Yeah. Yeah, that's all it is. Okay, so this is the mass you wrote right here. That is either the mass of the electron or the positron, right?
Yeah, they basically have the same mass, right? So
Right. So you're told they're at rest at the start, so they have no kinetic energy. So the question is, what is your initial energy? Energy initial is just 0.511 MeV for the proton, for the positron, and the same thing for the electron. So that's your initial energy, right? Because they're at rest. So kinetic energy is 0.
squared.
Okay.
Awesome.
And then and now what is the energy afterwards? Okay. The energy afterwards, you're told this is, so make this final, that's an F. It's 0.2 MeV plus 0.3 MeV. And then you don't know what that's a 3. That's just a lot. That's a terrible looking 3. There it is. Plus whatever the energy of the third one is.
Like something X or something. Yeah.
Yeah, right. But you know that the sum of those has to be that.
Has to be that, and then we rearrange to solve for that, and then once we get that energy, we can put it into
Yep.
this to get wavelength. And
Exactly.
yeah. Perfect. Yeah.
I would go HC over lambda. It's just quicker to do the calculation that way.
Oh yeah.
Yeah.
That's like the default thing in my head, and then I put in the right.
All right.
Yep. I got it.
And you remember what
right.
HC is?
What
1240
is the value of HC in megavolts? 1240. Okay.
1240 EV nanometers is H times C. Okay.
Did you? What is this exactly? Did you like square this or?
No, that's times 2.
That's
right?
times 2. Which is kind of
0.511 for the proton, for the positron, 0.511 for the electron, and you're just doubling it then. Yeah.
It makes sense. Yeah, I was like, why is it squared?
No, it's a times
So-
2. Yeah, little dot right there.
So we equate the energy, initial energy, final, and then I think I got 0.522. And then with that energy value, we solve for
Lambda.
the wavelength. Okay.
Yeah, that's it. All right, I'm gonna go.
Perfect. Thank you. Thank you.
See you guys in a minute.
Yep.
All right. Who's not back? We're missing. Up, everybody's back now. All right. So the moral of the story, hopefully you found each of the groups. Don't overthink these problems. Just think something real basic like initial energy is equal to final energy. Literally add the MEVs up. The 2 numbers that you need to know, I guess, are H times C, 1240 EV nanometers, and the rest mass energy of an electron, 0.511 MeV. Masses per C squared, but then you multiply by C squared. All right, group 1. Let's see, Anaya, who want to put that up real quick?
Yeah, I think he was projecting it.
Yeah.
You gotta allow me to share screen.
Oh, did I do that? Okay, sorry. Yep, I always forget. Go ahead. Should be up now.
Okay, so we didn't have any actual math. We just had to manipulate the equation E equals HC over wavelength because if it's the threshold, then you could forget about all the other stuff. And so we just solved for wavelength. And then, I mean, he said that we should keep it HC over 2 or over MC, 2MC squared, but we crossed out the C's and never went back.
You've got an expression. I mean, I can even do this though and get you a numeric value, can't I? Because it'd just be 1240 EV nanometers and then divide by 1.02 mega electron volts. So that's times 10 to the 6th EV. And then the EVs cancel. And so you get the expression is correct. Okay. But you can actually get a number out of this. And just for your reference, it's about 1.2 picometers. Remember, Compton wavelengths were of the order 20 to 30 picometers, much shorter for, that's as big as the wavelength could be for pair production to occur. Has to be smaller than that. All right, so you can actually get a numeric value. All right, group 2, which was Max and Sam. Were you guys group 2?
No, it was me and Sneha.
Sorry, okay. I had the wrong. They must be group 3 then. Yeah, they're group 3. All right.
I don't know if she wants to talk for this or not.
Yeah.
But here our equation HC divided by lambda set equal to 2 MEC squared plus the kinetic energy for the positron and then the kinetic energy for the electron. And then we just solved for one side, and then we solved for the left side, and we had to convert our picometers to nanometers. And then we
And
had
we converted that
to
energy
just
to
solve.
mega electron volt. Yeah.
Yeah, absolutely right. Everything they're doing here is correct. Notice, and the one thing they're told is that the kinetic energy of the positron is twice that of an electron. And so that's the key step is right there where they substitute in twice the kinetic energy electron for the kinetic energy of the positron. And then everything else are just numbers. It's converting correctly from MeV to electron volts. And absolutely right, when you're done, the electron has just a little over 1 MeV and the positron double that, because that's what the problem said, about 2 MeV. All right, questions on that one? All right, we're about a minute or so over here. Max, you're next. I guess you and this time it is you and Sam, I think, for problem 3. Okay, they're doing an annihilation problem.
So it produced 2 mega electron volt photons, so that's a total of 4 mega electron volts, which is has to be the energy of the positron and the electron. Subtracting the rest energy, 0.511, you get the kinetic energy of each, and they have equal kinetic energy. So
yeah, and that won't always be that way, but that's what you're told in this problem. Pretty straightforward. Add the energies up, add the MEVs up. All right, great. And last one, that was Prince and Saeed, right?
Yeah.
All right, loading here. All right, perfect. So yeah, pretty much what we did is we had to find the energy of a third photon. We were given energy of the 2 out of the 3 photons created. We found the total energy by here because, by multiplying the energies, it was an electron and a positron. Kind of did a rearrangement, found the third energy of the third photon, and plugged it into equals HF and solve for wavelength.
Yeah, exactly. And the only thing that made this problem, I guess, doable is they said we could have either given you what the initial kinetic energy was for the positron and the electron. We're told it's at rest, so the kinetic energy is 0. And so that meant it's just double the rest mass energy was your initial energy, literally just finding what that final energy is and converting it. Perfect. All right, any questions? All right, one of my least favorite topics is Rutherford scattering on Friday, but we'll look for that on the pre-lecture video and read that in your textbook. Here's a homework due tonight. One of the things some of you probably did, because a couple of you are finished, you noticed that the homework includes pair production. I'll slide it to tomorrow night to be due, since we're just doing pair production today, and the last of the 4 problems is on pair production. It looks like people who did it figured it out, but I'll give you an extra day on that. All right. Questions? Sorry, kept you long. We'll see you on Friday.
Thank you.
You bet.